On November 10, 1975, the SS Edmund Fitzgerald, a colossal carrier, vanished without a trace into the churning waters of Lake Superior. This was no ordinary storm, it was a furious gale, infamous in maritime history. But the question that has haunted generations isn't just that it sank, but how. The Fitzgerald was a symbol of strength and reliability, yet it succumbed to forces that remain a subject of intense technical analysis. Our journey begins with this profound mystery, seeking to understand the mechanics that turned a routine voyage into an unprecedented disaster. The Edmund Fitzgerald was an engineering marvel of its time, the largest vessel on the Great Lakes when launched in 1958. Stretching 729 feet, it was designed to carry immense loads of taconite pellets across the often treacherous inland seas. Its robust construction and experienced crew had navigated these waters for 17 years, completing thousands of successful voyages. This wasn't a fragile vessel, but a testament to American industrial power, built for the rigors of freshwater transport. Its sheer scale underscores the magnitude of the forces it must have faced. On November 9, 1975, the Fitzgerald departed Superior, Wisconsin, laden with over 26,000 tons of taconite. Its destination, a steel mill near Detroit. Initially, the weather was fair, but forecasts indicated a developing storm system. Captain Ernest McSorley, a veteran of the lakes, was well aware of the unpredictable nature of Lake Superior's moods. He chose a northerly route, seeking the relative shelter of the Canadian shore. This was standard practice, a testament to the respect experienced mariners held for these vast, powerful freshwater seas. Lake Superior is not merely a large lake, it's an inland sea, capable of generating conditions rivaling the open ocean. Its immense fetch, extending for hundreds of miles, allows winds to build formidable waves. Unlike oceanic swells, Great Lakes waves often have shorter periods and steeper faces, making them particularly dangerous for vessels. The cold water also contributes to rapid temperature drops and intense weather phenomena, creating a volatile environment where storms can develop with alarming speed and severity, catching even the most prepared off guard. As the day progressed, weather conditions rapidly deteriorated. A powerful low-pressure system deepened over the Great Lakes, bringing gale-force winds and heavy snow. The Fitzgerald maintained radio contact with other vessels, reporting increasing winds and waves. By afternoon, winds were gusting well over 50 knots, and seas were building significantly. This wasn't merely bad weather, it was evolving into a generational storm, one that would test the limits of even the most robust vessels and the experience of their crews. The lake was beginning to show its true, terrifying power. Around 3:30 p.m., the Fitzgerald reported its first major issues to the SS Arthur M. Anderson, another freighter trailing behind. Captain McSorley radioed that the Fitzgerald was experiencing a couple of working lights gone and a fence rail down. More critically, he mentioned that the ship was listing and had lost its radars. These details, though seemingly minor, pointed to more significant structural or operational problems. The loss of radar meant a critical reduction in situational awareness, particularly dangerous in zero-visibility conditions and towering waves. Large ships like the Fitzgerald are designed to flex under the stress of waves. This is known as hull bending. When a ship rides over a wave crest at its bow and stern, with the midsection in a trough, it experiences hogging, where the hull sags downwards. Conversely, when the midsection is on a wave crest and the bow and stern are in troughs, it experiences sagging, where the hull arches upwards. This constant, dynamic stress, especially in sequential, steep waves, can push a vessel beyond its design limits, leading to metal fatigue or even catastrophic structural failure. While ships are built to withstand expected wave forces, rogue waves are a different phenomenon altogether. These are disproportionately large waves, often appearing suddenly from an unexpected direction. They are not merely large versions of normal waves but are created by complex interactions of wave systems and currents, sometimes aided by underwater topography. On the Great Lakes, the constricted fetch and rapid weather changes can facilitate their formation, presenting a deadly, unpredictable hazard that can exert enormous, concentrated pressure on a ship's hull and superstructure. The danger is compounded when a ship encounters not just one, but a series of rogue waves. This sequential rogue wave scenario means the vessel does not have time to recover or redistribute stress before being hit again. Each successive impact can further compromise structural integrity, forcing the hull to bend and twist beyond its elastic limits. For the Fitzgerald, caught in a narrow trough between two powerful storm systems, it's plausible that such a sequence of immense waves could have delivered repeated blows, critically weakening key sections of the ship, especially the midsection. The Fitzgerald's 21 cargo hatches were crucial to its watertight integrity. Each hatch was covered by a steel lid, secured by 68 clamps and a tarpaulin cover. While designed to keep water out, their continuous exposure to flexing and twisting forces during severe storms could lead to deformation. If clamps failed, or the seals were compromised, even a small breach would allow water to enter the cargo hold. This ingress, slowly at first, would increase the ship's draft and reduce its freeboard, making it even more vulnerable to subsequent waves. Many maritime experts believe that the progressive flooding of the cargo holds, initiated by failed hatch covers, was a critical factor in the Fitzgerald's demise. As water accumulated in the forward holds, it would have caused the bow to ride lower in the water, a phenomenon known as trim by the head. This altered the ship's stability, increasing the stress on the midsection and making it easier for waves to wash over the deck. This vicious cycle, more water, more stress, more water ingress, could have led to a rapid loss of buoyancy and ultimately, structural collapse. Around 7:10 p.m., the SS Arthur M. Anderson hailed the Fitzgerald one last time. Captain McSorley replied, "We are holding our own." This was the final communication. Just minutes later, the Fitzgerald vanished from radar screens. The Anderson's captain, Jesse Cooper, looked out into the howling storm and saw no trace of the massive vessel. The speed of the sinking was astonishing, leaving no time for distress calls or lifeboats. It suggested a sudden, catastrophic structural failure, rather than a slow, gradual foundering. The immediate aftermath was chaotic. With gale-force winds and towering waves, the Arthur M. Anderson bravely turned back to search, joined later by a Coast Guard cutter and aircraft. They found no survivors, no wreckage, only scattered debris, life rafts, buoys, and other small items, confirming the ship had indeed gone down. The vastness and frigid temperatures of Lake Superior quickly sealed the fate of all 29 crew members. The search transitioned from rescue to recovery, uncovering only fragments of the mighty freighter's final moments. The discovery of the wreck months later, in two large pieces nearly 530 feet below the surface, launched a comprehensive investigation. The U.S. Coast Guard, the National Transportation Safety Board, and others conducted extensive analyses. Key areas of focus included the structural integrity of the hull, the condition of the cargo hatches, and the specific dynamics of the storm. The wreck itself provided chilling clues, confirming a catastrophic event but leaving the precise sequence of failures open to interpretation and debate for decades. Two primary theories emerged: structural failure and cargo hatch failure. The structural failure theory suggests the Fitzgerald either broke in two on the surface due to immense hogging/sagging stresses, or plunged to the bottom and broke upon impact. The cargo hatch failure theory posits that waves inundated the holds, causing a catastrophic loss of buoyancy and stability. It's likely a combination of these factors, with progressive flooding leading to a weakened hull, which then succumbed to the forces of a rogue wave, triggering a rapid, uncontrolled sinking. Before the Edmund Fitzgerald disaster, Great Lakes loadline regulations, while present, differed from those for ocean-going vessels. Load lines, painted marks on a ship's hull, indicate the maximum safe depth to which a ship can be loaded. These rules were less stringent on the lakes, partly due to the assumption that inland seas posed different, perhaps lesser, challenges than the open ocean. This perspective, however, underestimated the unique and formidable power of a Great Lakes gale, particularly regarding wave steepness and frequency. The sinking of the Edmund Fitzgerald served as a stark, tragic lesson. It highlighted the urgent need to re-evaluate loadline regulations for Great Lakes vessels. Subsequent investigations led to significant changes, including stricter requirements for hatch covers, coamings, and securing mechanisms. More importantly, load lines were adjusted to reflect the unique and severe conditions possible on the lakes, acknowledging that these inland seas demand the same, if not greater, respect for structural integrity and stability as the open ocean, especially in winter months. Beyond load lines, the disaster spurred broader improvements in Great Lakes maritime safety. These included better weather forecasting and communication systems, more rigorous inspections, and enhanced crew training on emergency procedures and ship stability. The analysis of the Fitzgerald's fate underscored the critical importance of a vessel's intact buoyancy and the need to prevent any uncontrolled ingress of water, especially in the challenging environment of the Great Lakes. The lessons learned, forged in tragedy, continue to protect mariners today. The SS Edmund Fitzgerald remains a potent symbol of the Great Lakes' power and the inherent risks of maritime travel. Its story is more than a tale of a ship lost, it's a profound case study in maritime disaster analysis, revealing the complex interplay of natural forces and engineering limits. The legacy of the mighty Fitz continues to echo in every strengthened hatch cover, every adjusted load line, and every updated weather alert, reminding us that even the most robust vessels are ultimately at the mercy of the sea's unpredictable fury. A legend, and a lesson, etched forever in the depths.